The other important nuclear reaction is the CNO cycle, for which there is a series of reactions. You see here, carbon captures a hydrogen, which is this one, forming a nitrogen and releasing a photon. The nitrogen decays into carbon, emitting a positron and a neutrino. This carbon captures a hydrogen, becomes a nitrogen 14, releasing a photon. This nitrogen 14 combines with another hydrogen, makes oxygen 15 and a photon. The oxygen 15 then decays into nitrogen 15, emitting a positron. And then this nitrogen 15 combines with another hydrogen and produces carbon 12 and helium. So the net product of this is that CNO was catalyzed to produce a helium. You can see that nitrogen was produced here, carbon was produced and consumed, nitrogen was produced and consumed, so was the oxygen and the nitrogen 15. If you sum all of the processes, what happened was that you had 4 hydrogens that were combined to produce a helium. The nuclear burning rate for the CNO is, and in this expression here, X of NCO is equal to the concentration of carbon plus the concentration of nitrogen plus the concentration of oxygen. It's interesting to evaluate here epsilon for the proto-proton chain and for the CNO cycle using appropriate values to the center of the sun. If you substitute for the center of the sun density about 150 grams per cubic centimeter, temperature about 15 million Kelvin, the mass fraction of hydrogen 0.74, and mass fraction of CNO equal to 2%, then you find that for the sun, the energy production rate of the proto-proton chain is about 82 ergs per second per gram, and for CNO is about 6.4 erg per second per gram. So the proto-proton chain dominates in the sun by about a factor of 10. However, you should notice that the CNO cycle has an exponent 153.3, whereas the proto-proton chain has only a 33.8 factor in the exponential. That is significant, so therefore CNO is very sensitive to the temperature, much more sensitive than the proto-proton chain. So this shows the energy production rate from the proto-proton chain and for the CNO cycle. Indeed, at 15 million Kelvin, the temperature of the core of the sun, it is the proto-proton chain that dominates, but not much beyond, you start to have the CNO cycle take over at about 17 million Kelvin. This also brings out a general feature of nuclear reactions. The temperature sensitivity is determined by the exponential in the form of the nuclear burning rate, which in turn depends on the charges of the nuclei involved, because it is determined by the Coulomb barrier. The stronger the nuclear charge, the stronger the Coulomb barrier, and thus the higher the ignition temperature and the more temperature sensitive the reaction becomes. The CNO cycle is more temperature sensitive than proton-proton, and the sensitivity only gets stronger as we march up the periodic table.